Hi students, in this first video for online lecture 15, we are now going to talk about limiting reagent and percent yield. So let us talk about limiting reagent. A stoichiometric amount is one of the most important things that we are going to deal with in our reactive chemistry and stoichiometry. Stoichiometric amount means that we have exact proportions indicated by the balanced chemical equation. This means that if we need 2 moles of something and 1 moles of another, that means that we have those amounts and they are going to run out at equal times. However, that is normally not the case. This is what is going to lead us to the limiting reagent. The limiting reagent is the reactant that will be used up first in a reaction. So let us go ahead and look at this example. First off, we have our balanced chemical equation of having 2 NOs plus O2 going and yielding our 2 NO2. So let's look at our schematic on the right. Notice that in our previous part in before the reaction is started, we have NO and O2. But then as the reaction goes to completion, you will now see the biggest issue. Notice that we are going to have some of our product that is going to be circled here in red, but we are not going to get as much product as we expect because we have run out of our NO. This means that we are going to have unreacted oxygen, circled in blue, that has not been used in our reaction. So let's talk about a few things and why this would happen. One, we might have what we call in excess. In this case, that is going to be the O2. We like to use cheap reagents in excess, so that way we can force the reaction to go completion and to full amount of products. The other thing is, why would we have a limiting reagent? Well, it may come down to the expense of that reagent. In many reactions, we are going to use the most expensive reagent as our limiting reagent, so that way we are going to get all the product that we expect for that reagent. So this is the chemistry side of it, but this can get a little cumbersome and hard to understand. So let's take this back to something that, at least from my childhood, is very easy to understand when we are trying to deal with the limiting reagent. And that is the GI Joe. So we are going to build GI Joes in an idea using a balanced chemical equation. So for a good GI Joe, you need to have 2 arms, 2 legs, a body, and a head. So this is actually can be created using what we can think of as a balanced chemical equation. 2 arms plus 2 legs plus a body and a head gives us a quality GI Joe. So one of the things that happens in here is that back in my childhood, when my brother would go to school, I would try to disassemble his GI Joes to build other GI Joes. So one day while he's at school, I was able to disassemble many of the GI Joes. So now the question becomes, as 3 o'clock rolls around and my brother's coming back from school, I have a pile of 90 arms, 72 legs, 48 bodies, and 62 heads. How many GI Joes am I able to go back and reassemble? So notice that if I have 90 arms and I go back and look at my balanced chemical equation, I need 2 arms for every GI Joe. That means just on arms alone, I could go and build 45 GI Joes. Well, now let's go ahead and look at the legs, and you will see that I have 72 legs. So if I go look at my balanced chemical equation, you will see that I need 2 legs for every GI Joe, and now I am able to only build 36 GI Joes. So this means of my 36 GI Joes that have legs, they will also have arms. But then there are going to be 9 GI Joes that have arms, but don't have legs. So we've got to be very concerned about that because we need to have fully created GI Joes. So if I look at my bodies, notice that I have 48 bodies. So that means that I would get 48 GI Joes. And finally, I have an abundance of heads, and you'll notice that I could build 62 GI Joes with heads alone. So what does this mean? let us go and see the smallest amount of completed GI Joes that I can build. So notice that that is 36. You see that number right here. 36 GI Joes are going to have arms, legs, a body, and a head. That is a completed GI Joe. That is a completed molecule. So then now you can also see that for the next 9, getting up to 45, I'm going to have arms, a body, and a head. I have no legs. That is a problem. So then the interesting part is, for the next 3, I'd have a body and a head. But then after that, you'll notice that I have 14 heads left over. So what did I learn from this? I had no idea at the time that I was understanding what a limiting reagent was. All I was concerned about was not getting a beating from my brother because I had a whole bunch of his broken GI Joes laying on the floor that I couldn't reassemble. The other thing I learned from here is I was not going to be a surgeon, and that is how I ended up with a PhD in chemistry. So let us talk about this now in a chemistry sense. Now that you understand how to build things with parts that may not be equivalent, let's look at it in a chemistry route. So we're going to build urea, and it is prepared by reacting ammonia with carbon dioxide using the balanced chemical equation that you see. In one process, I have 637.2 grams of ammonia, and I have 1,142 grams of carbon dioxide. So first thing we need to do is see which of the 2 reactants is our limiting reagent. But I want you to take notice in here, using the ideas of stoichiometry that we saw in the previous lecture, we are going to need to go from grams to moles to moles. We want to stop at moles because, as you can see in part B, we are going to need to go to the desired unit of our urea. So what I would like to do for part A is go from grams to moles of urea and stop there and see which one would produce the fewest moles of urea. So in this case, let us go ahead and start with our ammonia. So we have 637.2 grams of my NH3. We need to get our unit conversion factor so that we can get to our moles. So that is 1 mole of our NH3. I need the molar mass of urea, so that is going to be 17.034 grams. And then finally, we need to use the balanced chemical equation ratio. Notice that I get 1 mole of urea for every 2 moles of ammonia. So now we have calculated the moles of urea. The reason we want to do this is this gives us a very nice stopping point where we can compare apples to apples. We cannot compare our apples to oranges when we're dealing with our moles of one reactant and moles of another reactant because we have to go to the same place in our balanced chemical equation. So if I do this math, you will get a value of 18.70 moles of our urea. So now let's go ahead and look at our other reagent. So that is going to be our carbon dioxide at 1,142 grams of our CO2. So now we need to go on a similar path and say that 1 mole of CO2 has a molar mass of 44.01 grams. And now you will see that this ratio is 1-to-1 from our balanced chemical equation. So I will get 1 mole of urea for every 1 mole of my CO2. So if I do this math, you will see that I can form 25.95 moles of urea. So now, which one can form the least amount of moles of urea? And as you can see here, our limiting reagent is going to be our ammonia. So you are going to want to select the reactant that forms the fewest moles of product. So that is going to be our answer for A, and we would correctly select the ammonia. So now let's go ahead and look at part B. Calculate the mass of that urea formed. Well, the nice part about B is we've done most of the math. We have gotten to this point where we know how much urea can be formed from our limiting reagent. So the only thing we have to do after this is go to grams of urea. So in this case, I will take my 18.7 moles of my urea, multiply it by the molar mass. So that would be 60.06 grams of urea in 1 mole. If I end up doing that, you will get a value of 1,123 grams of our urea. So it's one of those things that if you do the process very well for A, you'll have done most of the work for part B, and that is what we want to do. So now let us go to part C, which can be a little bit more frustrating, but we've done most of the math. How much excess reagent in grams is left at the end of the reaction? So we now know that our excess is going to be our carbon dioxide. So how do I know how much carbon dioxide is left over? Well, notice that when I do this reaction, I would have been able to form 25.95 moles, but I wasn't able to form that. I was only able to form 18.70. So what we want to do is go and take the difference of that. So I can go and take 25.95 moles of my urea and subtract our 18.70 moles. And this is going to give us the number of moles that we were not able to form previously. So if we do this math, you will see that I end up getting 7.25 moles of urea that the carbon dioxide could form, but wasn't formed because we ran out of the ammonia. So now what we need to do is go backwards and calculate our mass of carbon dioxide. So what we are able to do is use our balanced chemical equation and say we get 1 mole of CO2 for every 1 mole of urea. Then I need the molar mass of my carbon dioxide, which is going to state that I would get 44.01 grams for every 1 mole of CO2. If I do this, I will get a leftover mass of unreacted carbon dioxide at 319 grams of my CO2. So it's really important that sometimes you want to calculate how much leftover material you need in order to look at the efficiency of your reaction. Now that we know that we are going to run out of certain things when doing our reaction, we also have to look at our percent yield. So a theoretical yield is the amount of product that would result if all the limiting reagent is used. This would be the maximum obtainable result. This means that every single atom does exactly what you want, how you want it, and forms product. This is highly unlikely. What we actually get is the amount of product that you would get in the process in the lab. So the interesting part is that we can calculate our percent yield. That is our actual yield, what you get in the lab, divided by your theoretical yield, multiplied by 100%. Why is it not always 100%? Well, let's be honest. Not all atoms and molecules do what we want. They may form what are called side products. This means that they react in a different way based off of the reaction conditions, and so they go and do what they want, not the reaction that you intend. The conditions may not be perfect. We could have moisture. There could be a temperature change. There are a lot of reaction conditions that you would have to observe to get an optimized yield. You might spill something or make mistakes. One of the biggest issues with undergraduate students is they blame it on human error. Yes, human error does happen, but there are many other reasons for a lower actual yield than just blaming it on your lab partner. The other thing you need to do is you verify with your calculations beforehand. When doing any stoichiometry or reactions in a lab, it is best to go and do all of the theoretical yield calculations prior to doing any benchtop exercise. Then when you have completed all of your experiments, then you can take your yield and see what your percent yield is when you have finished the reaction. So let us go ahead and try this industrial process. Titanium is a strong, lightweight, corrosion-resistant metal that is used in rockets, aircraft, jet engines, bicycle frames, and most importantly, Lieutenant Dan's new legs in the movie Forrest Gump. It is prepared by a reaction of titanium 4-chloride with molten magnesium at a temperature right around 1,000 degrees Celsius. You can see the balanced chemical equation, and I now give you masses of both titanium chloride and our magnesium. So the first thing that we need to do is go out and calculate the theoretical yield of the titanium in grams. Seeing that you're given both masses of both reactants, you are probably going to have to do a limiting reagent problem to start off this exercise. So let's go ahead and do that first. So let us start with our titanium chloride. So we have 3.54 times 10 to the 7th grams of our TiCl4. We then have to go to moles. So we have 1 mole of that compound having a molar mass of 189.667 grams. And then finally, we need to look at our balanced chemical equation, and we notice that we get 1 mole of titanium for every 1 mole of our titanium chloride. So if we do that, we will end up producing an amount of 1.87 times 10 to the 5th moles of titanium. Is this our limiting reagent? Well, we don't know yet. We have to go and do our other reactant. So let us go ahead and look at our magnesium, which is 1.3 times 10, or 1.13 times 10 to the 7th grams of my magnesium. You need to get the molar mass of our magnesium, which is 1 mole being 24.305 grams. And then finally, notice that I get 1 mole of titanium for every 2 moles of magnesium. This comes from our balanced chemical equation. So if we do this math, you will end up getting 2.67 times 10 to the 5th moles of titanium. So now, which one is our limiting reagent? As you can look, the titanium chloride is going to be our limiting reagent. So now what we are able to do is go and take that number of moles, convert it to mass of titanium, and we will be able to think and calculate our theoretical yield. So let's go ahead and do that. So we have 1.87 times 10 to the 5th mole of titanium. We need to go and multiply that by our molar mass. So that is 47.867 grams for every 1 mole of titanium. And you would get a theoretical yield of 8.95 times 10 to the 6th grams of our titanium. So that is the maximum number amount that we should get if we do an absolutely perfect reaction. So let's go ahead and look at B. Notice that I don't do a perfect reaction. I only get 7.91 times 10 to the 6th grams of titanium. So how can I calculate this percent yield? Well, I will go and take my actual yield of 7.91 times 10 to the 6th grams and divide this by our theoretical. So in this case, that would be our 8.95 times 10 to the 6th grams. And we are going to multiply this by 100%. If we do that math, you will see that you get a value of 88.3% yield. Percent yield is often also called reaction efficiency. So if you see problems in which it says it is 88.3% efficient, understand that you are dealing with your percent yield. Our final example comes from the fall of 2016 exam, and that is going and creating sodium sulfide. So it's actually used in the leather industry to remove hair from hides so that you can make high quality leather. So we have our balanced chemical equation, and now you will see that I have 15.0 grams of my sodium sulfate and 7.5 grams of carbon. I want to calculate the percent yield if I produce 11.2 grams of my sodium sulfide. So how do I go and do this? Well, let's go ahead and try and calculate our theoretical yield and our limiting reagent. So first things first, I have 15.0 grams of my Na2SO4. I need to go and calculate the number of moles. So that is 1 mole for every 142.04 grams. Then I need to go to my balanced chemical equation, and you will see that I get 2 Na2S's for every 1 mole of Na2SO4. And this will give us a amount of 0.211 moles of my Na2S. So now what I need to do is go and check my other reagent. So if I say that I have 7.5 grams of carbon, what I need to do in this case is say that 1 mole of carbon is 12.01 grams. Now you'll see that I get 2 Na2S for every 4 moles of carbon. So if I do this, I will get a calculation of 0.312 moles of my Na2S. So which one's going to be the limiting reagent? Well, that is going to be my sodium sulfate, which is at the top. So now what I need to do is take my 0.211 moles of my Na2S. You guessed, I've got to go from moles to grams. So in this case, I need to take 78.04 grams for every 1 mole. And I can now calculate my theoretical yield, which should be 16.48 grams of my product. So now that I have my theoretical yield, I have an actual, and I can go and get my percent yield. So I will take my 11.2 grams divided by my 16.48 grams, which is going to be my theoretical, and I would multiply it by 100%, and you will come to see that I get a value of 67.9%. So this means that this reaction has an efficiency less than 70%. In this video, you have seen some complex calculations dealing with the stoichiometry to show us not only the limiting reagent, but our reaction efficiency and our percent yield. Anytime that you are doing any work in the lab with a brand new reaction, you are expected to do these calculations. Have a great day.